Welcome back to Joe's Computer Museum, where we left off with the project was a 16-bit hexadecimal address converter that would be able to take the 16-bit address bus of the 6502 and show me what was on the address bus in hexadecimal so I could see what the computer was doing. Since we saw you last, I made a little bit of a change to that decoder, so let's take a look at that. What I did basically is I added an extra module to the decoder here to show the data bus, the 8 bits of the data bus. Just a couple extra modules here, a couple more ROMs, wired up basically identically to this, so there's no real change in the schematic other than it's a larger device now. It has 6 pieces instead of 4. And the idea behind this is that I can hook these 8 wires here to the data bus of the 6502 and not only see what address is being fetched, but I can also see the data that's being pulled out. You know, it turns on, it works basically exactly the same as the other half, so when we get that hooked up, we can actually see what's going on. But that's not what we came here to look at. We came here to look at the actual 6502 computer, so let's bring that in and show that to you. So there we are. There's our very, very basic 6502 based computer. It's not actually a computer yet, not technically, because we don't have real RAM, we don't have real input-output capability, but we'll be getting to that soon. Now, there's a lot of bits and pieces here. It's not just a processor, there's a whole bunch of other extra support circuitry, so let's go through all of that piece by piece and show you what's going on. So the first thing is this half of the board here, these 2 chips and all of this support circuitry here. This is our power on reset or auto reset circuit. Basically, it's a 555 timer combined with an inverter that when it receives power, it will strobe it's in a monostable mode, so it'll strobe a single pulse out to the reset pin of the 6502. It's set up with a 10 mic capacitor and a 47K resistor here that in combination give me approximately a half a second of signal or half-second pulse, which should give us plenty of pulse to get the machine bootstrapped and working correctly. Basically, that comes out of here, out of this pin, pin 3, which is the output pin of the 555 timer, comes into an inverter. What that does is it inverts the positive pulse coming out of the 555 into a negative pulse, which is what the reset pin on the 6502 and all of the 6502 standard circuitry requires, and which will then reset the system. Quick reason why the 6502 needs that. When the 6502 powers on for the first time, and many of its support chips as well, they will all power up in a quasi-unknown state. Basically, it's just a monolithic slab of void when you turn it on, and it doesn't get set to anything when it's powered on. But when you pull the reset pin low, it basically yanks all the circuitry back to where it needs to be internally and puts it into a known state. So that's why you have to do the reset on that. The reset circuit I used here is similar to the one that's in the JCM-1 computer. It's also similar to the reset circuit that's on the floppy controller of a Disk 2 and an Apple II. It's pretty straightforward. Nothing super complicated there. I did add one little thing to the reset circuit here, and that is this little LED. This allows me to visualize what the reset circuit is doing. So when that pulses output, that LED will light up, and I can see an actual reset circuit is being pushed out to the system. Now let's go over here to this section. This is the actual processor, the Synertec 6502A. This specific chip was pulled out of an Apple IIe unenhanced, and I'm using it because I happen to have it. I'm eventually going to be upgrading that to an actual 65C02 because it has a little bit better compatibility, better reliability, better operational characteristics, and I can, if I decide that I want to see if I can super speed the machine up to multiple megahertz, those processors can do better. This guy, he's stuck at 1 meg. So let's talk about some of these things here. This right here, of course, comes out of this, out of the inverter over to here, and then into this line right here. This is our reset pin. The reset pin needs to be pulled high, so we have a, I believe that is a 220 and no zeros. That is a 220 ohm. 200 and 2 zeros. That's a 2K. This capacitor here, or not capacitor, resistor, pulls this pin to positive. And then what happens is when the negative reset comes through, the negative reset has less resistance, so that signal is going to take precedence and it's going to pull the pin low, and then when it's done, it pulls the pin back high where it should be. That's something that, it's a trick that, or a problem I ran into, something I learned while working with these circuits, is that input circuits on chips do not like to be floating. They have to have either positive, negative. They have to have some signal on them. If you leave them floating, they do weird things. They don't work right. So you got to make sure you couple pins that require inputs or outputs to what they need to be. Down this side of the processor here, this is our standard power pin. These pins right here, and let me pull out my data sheet so I can remember exactly what we're talking about here. This is the ready pin. We're not using this right now. We may never end up using it. This is our phase 1 pin, which is basically an inversion of the actual clock pin. I have an LED connected to that so that as the CPU receives its clock, it blinks back and forth because it looks neat. I don't really need to have an LED connected to it. I just wanted to. This right here is our IRQB, as it's called. B meaning negative, according to the documentation. I'll just call it the IRQ line. The next one is an MLB, which we will not be using at all. This processor is actually, there's nothing on that pin. This is the 65CO2 that has that pin, but we'll be ignoring it. This is our NMI, our sync, and our VDD lines. The VDD being the actual power. This is ground power. The sync line is basically left to float, and again, the NMI is pulled high. These IRQ and NMIs, those are the interrupt request and non-maskable interrupt request lines. When those go low, it tells the processor to go fetch its reset vector and go jump off into la la land and respond to the interrupt that it's received. The rest of these pins here are the address bus. Nothing's connected to those right now. We'll be getting to that soon. Again, 4 pins here. Address bus. We'll get to that. These pins right here are the data bus. We got a funky little connector on here. Normally, these guys would be connected to a data input from RAM or ROM. But because we don't have RAM or ROM in this computer, we got to feed the computer or the CPU something. So it's a little bit hard to see, but basically this is hardwired to 111-01010. The red's on this side, the black's on that side. 111-01010. When you convert that to hexadecimal, that is the character EA. Keep that in mind if you're 6502 programmer. You know what that means. If you're here along for the ride, I'll explain it in a little bit. There's a few extra pins in here we're not using. Some are not connected. Some are the read-write and all of that stuff. We will be getting to those pins later on. These pins are used to signal to the computer or signal to the other bits and pieces of the computer, hey, I'm the CPU and I don't need to be doing anything right now. You can have the bus. So we're going to be coming back to those pins eventually. This pin, this wire coming right over here, this is our phase 2 clock. This is the master clock that drives the oscillation and the operation of this chip. So I have that jumping over to this side board. Basically, when this receives a down transition, a falling transition, a positive to negative transition, it cycles the processor. Of course, this being the invert of that, so when you turn this on, you can see those blink back and forth. Like police lights or something. I don't know. I should have made that one blue. It would have been red-blue. That would have been cool. Anyway. This little guy right here is stupid. That's just a power light. That reminds me that the computer is on in case other things aren't working right. If this little white LED is bright white, that lets me know the machine has power. Coming over to this section of the circuit, this is our oscillator. oscillator bank. I set up 3 different oscillators on this so I can run the machine at various different speeds to help me in diagnosing things. This oscillator right over here is our super slow oscillator. This oscillates at about 1.6 hertz or so. This is a 555 in astable mode, which means it works in conjunction with this capacitor resistor circuit, those guys right there, to cycle back and forth and back and forth and back and forth, on, off, on, off, on, off, on, off, over and over and over and over and over again. Of course, we have our red output coming to over here. And we also have an LED in series with that, so that we can say, hey, you know, we can see that that's cycling and that this oscillator is actually functioning. This oscillator is our slow oscillator, this being super slow. This oscillates at about 150 hertz, give or take, 145, somewhere in there. Basically, this allows us to run the clock fast-ish, but still slow enough that we can actually see something happening on the computer. So if we want to speed up operation during diagnostics. And the final oscillator is going to be our final oscillator when we're done, I believe. I don't know, I might change my mind later. This is a 1 megahertz crystal can. Basically, it's a self-contained oscillator. You give it positive and negative, and it gives you a 1 megahertz square wave out. Again, I have it connected to a light just like these others two, so we can see that what it's doing. Now this one you can see blink pretty obviously. It's just like on, off, on, off, on, off. But this one here and this one here, because these oscillate so fast, they basically, the light just looks like it's on. You can't really see it blinking. I have the outputs of these come into, you know, a few little pins in series, so I can actually move this while the machine is running to these different frequency bands and put it back down while I'm playing around with it to see what it looks like when the machine is running. Well, that's the basic introduction to the computer. So let's actually connect our hexadecimal display here to the computer, power it up, and see what we get. So this is the low part of our address bus. This guy goes right here. This is the high part of the address bus, which goes in here. I gotta twist that out of the way. High part of the address bus. And this is the data bus. So the data bus needs to go here on, connected to where the data input would go to the processor. Input or output, actually. So we put that together. Sneak those together real quick like. Now, can we see the output of that? Yeah, we got some cables in the way. Let me see if I can route these a little better so you can see what it's doing. Maybe we can move this over here and we can, I don't know, route this over like this so it's out of the way. There we go. Now you can really see what it's doing. So, these boards aren't bonded by power together yet, so we need to plug our positive lead over here, negative lead over here, and that should be it. Let's turn it on and see what the heck happens. Now, we do have one little problem, actually a couple little problems. One is a wiring issue. You can see that this lower LED doesn't light. That happens sometimes on this guy. That would be second pin down here. Sometimes, you know, this thing's a little squirrely. Let's see if I can get that working. Doobie doobie doo. Technical difficulties. That happens sometimes. We'll take a little pause while I fix this if necessary. Yep, we just got a loose wire here. Looks like it's this one. This one. Wow, that entire connector is just wonky. There we go. We got it working. And we're back. So, you know, it's breadboarded. Things don't always work terribly well on breadboards. So, let's explain what this is doing here. We had two little hiccups when we turned it on. First off was our display, which I don't blame it too much. You know, these ROMs don't fit in the breadboards too perfectly well. The other problem we had is this thing did not start where the reset vector said it should have been. The reset vector being like FF, FE, and FFFF or something like that up at the high end of the memory space, which should have told it to go to a specific memory location, but it just started at 0 and started counting up. The reason why that happened was this, is because, you know, the CPU starts in an unknown state. If it doesn't set up correctly when it boots up, it usually just starts executing from 0000 and just cycles up. The reason why this did not turn on correctly is this. This reset circuit here has a approximate 0.51 second cycle time. And our oscillator, the slow oscillator I have it hooked up to, has like a 0.47 vibration, a 0.46, somewhere in there, vibration time. So this guy is slightly faster than the reset circuit. Now, in this current configuration, doesn't matter. This is going to be my final reset circuit. This is not going to be my final oscillator. I'm not too worried about that. But basically what that means is this started cycling the processor before the reset signal could take hold, before the CPU could recognize that there was a reset signal there and do something about it, basically. So if we actually press and hold this, you'll get to see that half-second pulse. You'll see the light turn on, and we should see the CPU reset itself. There it goes. So the reset vectors in C and D, excuse me, FFFC and FFFD. And you can see that it fetched the address EAEA, which is the same as that. Weird. Now let's explain what it's doing. The reason it did that is because we have the data bus hardwired to EA. When the CPU hits a reset vector or an NMI or an IRQ, it goes up to some of those high memory values to just fetch an address out of those memory values and unconditionally jump to what's in that memory value. Well, what is in the memory value of this computer at all times right now? EA. We have the data bus hardwired to EA. So it jumped to EA and started executing code. Now, why did we select EA? Well, those out there that know the 6502 know why I've done that. The EA is the instruction for the 6502 to do nothing. It is a no operation instruction. What this means to the CPU is that do nothing, go to the next instruction, and execute the next instruction. Since we always have EA on the data bus, the 6502 will continuously and forever execute absolutely nothing over and over and over and over again forever. What does this allow us to do? Well, that allows us to set up the computer in a very simple free run mode that allows us to see what's happening on the machine. And we can see that it's doing that. Now, let's play around with the speed. So we're running at approximately, a 1.6 hertz, or yeah, basically 1.6 hertz. But let's pop the guy over to here and let's turn it up to, I don't know, 150 hertz and see how fast it flies. There we go, and it is zooming off to the races. And you can see I got some of the LEDs are blinking a little weird. I must have some sort of signal isolation issue, or I might need a decoupling capacitor put in here somewhere that I forgot. So you can see it flies by pretty gosh darn fast. You can barely see what the least significant digit here is doing, and these clock up at a seeable speed. But what happens if we put it on 1 megahertz? That thing is screaming. It is moving through the memory space somewhere around 16 to 20 times per second. It's moving so fast. And the only digit you can actually see oscillating is this one right here, the most significant digit. The rest of these are oscillating so fast and cycling through their values so quickly, you can't even see what the machine is doing. In real operation, this is similar to what you would see if you were to hook up a device like this to a 6502-based computer running at about that speed. It would be flying through memory so fast, and these values here would be changing so fast you wouldn't be able to see anything the machine was doing. But that's okay. So let's go ahead and make it slow again. And stare at our blinking lights and watch them blink back and forth for a while. That's neat. Well, we have the base core of the computer up and running. We have the 6502 wired up with the correct configuration to be able to output what's on the data in the address bus and be in a mode that we could potentially, as a next step, start hooking some memory into it, see what that does. We have a good power on reset circuit so that when we get this up to speed and connected to an actual high-speed oscillator, it will auto reset and start executing from the right location. And we have everything basically set up and ready to go for the next step. That next step, I'm pretty sure, is going to be connecting some ROM up to the computer to give it something to execute. Not sure we're going to have it do yet because I don't really have any input or output out of the machine, but maybe we'll just have it spin in a loop for a while. We'll see. Before we let you go, I do want to go over a couple other little details of the machine. Let's go ahead and bring in the schematic here and get this in focus if we can. Can you focus for me? There we go. So, as I said, as I was showing on the breadboard, we've got three different sections going on right now. We have the CPU here, obviously. We've got our data bus wire to EA, no operation. We got our address lines going out to our hexadecimal display. And of course, we also have the data lines going to the hexadecimal display as well. That's just not shown here in the schematic. Over here, we can see our decoupling capacitor, and we can see the ready IRQ, NMI, and VCC lines pulled high, and our ground line pulled low as it should be. And then here we have our reset line, which comes over to our reset circuit here. But our reset line with the 1K pull-up resistor to keep it positive, keep it from floating, and then when it actually resets, it gets a negative pulse. Our simple reset circuit here with a 5 volt here to pull this high when we're not pulling it to ground to do the reset or when it's not triggering. We've got our reset pin as well to the 555 pulled high because it needs that reset pin pulled high to say, hey, I'm running. Right here is our timing circuit. This 10 mic capacitor with this 47K resistor gives us that approximate half second discharge time that we need for the 555 to work. So when we pull this short, this causes a trigger to receive a little burst of energy from ground, pulls it low, causes this to trigger and reset, and it sends a square wave pulse out. Positive square wave pulse goes out to the inverter, which then pulls it low and sends a low signal over the reset pin to reset the processor. Of course, we have our oscillator up here as well, which we described. This is just a very basic guy running in monos or in astable mode with these two devices right here, basically timing this with whatever variable resistor value and capacitor value I wanted to put in there to get the frequencies that I wanted. And that is all we have to it right now. Other things that I wanted to talk about, I had some questions in the comments from the previous video about some details about how I made the hexadecimal address decoder work. I'll go into a little bit more details of that right now since I got everybody's attention. The hexadecimal converter works basically by having a truth table in these ROMs. I got these 1 megabit ROMs or 128 kilobyte ROMs off of Mouser for about, gosh, what did it cost me? They were actually about $1.97 a piece. I said they were 99 cents a piece. I had forgotten the price. But still, that's incredibly inexpensive. It's still cheaper than some PICs and microcontrollers out there. And basically what I did is, to get this working, I effectively mapped the ABCDEF, whatever, the common A, B, C, D, E, F, and G names for the pins on these guys to specific pins on my ROMs. So, you know, I mapped this to pin 0 on the ROM, and that to pin 1 on the ROM, and to 2, and to 3, and to 4, and 5, 6. I don't remember exactly why I did it in this order. It probably had something to do with ease of wiring when I was breadboarding it. But basically, so like this guy here, for example, pin 1 or pin E on this connects to pin 2 of a specific ROM there. And once I had this figured out of what I wanted each, it's not pin, it's each, byte value, data bit value. It is a pin value, but whatever. Once I figured out which each one of these was, then I wrote down a truth table, which, I do not have over here in my massive pile of data sheets. Actually, I might have it in here. Yeah, I do. I was playing with a truth table here. I think I ended up changing it eventually. I don't think it ended up being this. But I wrote out a truth table to get the actual byte values that would be required to turn the lights on that I wanted on for each value. I then turned those bit values just using the calculator in Windows 10, because it can instantly convert bit inputs to hex and to decimal and everything. It's pretty cool. Just converted those to hexadecimal values. Then I used the Mini Pro Logic Programmer to program those. And if you want to hold on for just a second, I'll go grab that and show that on camera. This is the Logic programmer I used to program these guys. It's a Mini Pro TL866. Absolutely common as dirt. They're everywhere. They're insanely cheap. They cost like under $20 or something like that. I don't remember exactly. Again, I probably said the wrong number like I said with those, so go look that up and yell at me in the comments for giving you the wrong price, but that's fine. Very super inexpensive programmer. You just install the software. The software works on just about every version of Windows out there, including Windows 10. And you put your chip in, you pick the chip that you're trying to program out of its database, and then you flash it. Now, the cool thing with this is it allows you, it has a built-in hex editor right in the interface. So I effectively built the ROM from scratch by just typing in the window and typing the hexadecimal values right into the screen that I needed, that I had written down. And then I flashed my ROMs, plugged them in, wired it up, and they basically worked the first time, aside from the little tiny breadboarding wiring glitches that I was having here and there. Basically did the same thing for this. After I had wired these up, I had saved that ROM. Over to a file that I was then able to just load up and load into these and do the exact same thing. I had to wire it slightly differently to connect it. So basically, what happens is, when the address bus comes out, when any 4 bits of the address bus comes out, it's going to select 0 through 15. The value 0 through 15 is the memory address for each one of those chips. And in 0 through 15, I have the value I want. Location 0 has the byte value that corresponds to the lights, which would be, in this case, which would be like A, B, C, D, E, F, in order like that. In the truth table here, A, B, C, D, E, F, like that, skipping these other lights we don't need. And it would just light those bits up. It would just light those up. And then, 1 would have these 2 in those byte values, then 2 would be those, and it would just do that. Set it up all across, wire it up, hook it up, and it just works. Well, that's all for today's episode. Next episode, we're going to look at putting some ROM in this machine. Maybe some other surprises, I don't know. We'll see where it goes, and see if we can get the 6502 computer executing code. Well, that's all for today's episode. While you're here, check out some of my other videos, and remember, 8 bits are all you need.